Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about Chinese nuclear battery. It's getting all the headline right now, so let's dive deep into it. So before we dive deep into the battery, we have to understand the core, what the hell is happening. So in simplest term, E equal to mc square is the most powerful reaction, quote unquote, that we have. Basically, the most powerful source we have. Anything that gives a boatload of energy generally is using E equal to mc square. As of now, as of known science, nothing exceeds this. Even matter, antimatter, same thing. So how can we reach this point? Well, you have three primary options of getting this sort of power. You have fission. Basically, you are taking a big atom, a very heavy atom, and you are divorcing them into two small atoms. That gives you a lot of energy. And then you have fusion, even worse thing, where you take two happy small atoms and you force them into a marriage. That gives really big boom. Then you have radioactive decay, meaning something loner, which is not in a stable state. It's like way too hot, basically, and it tries to, quote unquote, evaporate its material away, basically the M part, and gives off the energy. So that's how we get basically E equal to mc square. Now, what is the format of the energy? Energy does not mean just lol. What is the package of it? Like, who is the energy carrier? You also have to understand that. So if you have these three sources, there are only four possible energy packets that are available to you, meaning available to science in order to dump the energy. First you have alpha, then you have beta, then you have gamma, then you have neutron. Now, alpha is an easy puppy because it's a freaking nucleus. It's a naked nucleus. So it's a very charged particle, positive charged particle. So it's very easily stopped because it interacts with, well, everything. Atoms, electron cloud, it interacts with that, stops, wabam. Then you have beta. Beta is basically electron, a naked electron, so to say. Now, because electron is much smaller than the nuclei, it can go through quite a bit. It does have a bit more penetrating power, but because it's charged particle, it does interact with the electron cloud. Small size does allow it to go further, but because of the charged particle nature, it does interact with it, so it does not go too deep. So one will be stopped by, let's say, basic paper. Another would be stopped by a aluminum foil. Now, do you have to worry about it? Unless they enter inside your body, basically you eat something that is giving off alpha or beta, you are safe. Your body should be able to handle these things unless there are too much of it. So you should be fine. Your dead skin cells should be able to absorb alpha and beta without poofing you. Then we enter gamma. Now gamma, it's a bit hot puppy. So gamma is basically photon. Photon is the energy carrier here. Now, problem with that is photon is way too small. If you think electron is small, photon is like, nah, bruh, it's too small. It's just an energy packet. So it travels very fast and very far deep into it. It will interact with electron cloud. That's the good news, meaning you can put boatload of material in there to stop it, but you need boatload of it, meaning you need lead level of things. You need like some serious thickness in order to stop it. And then we have to reach the final puppy, that is neutron. Now, if there is a neutron source, run. There is nothing else to do, just run. Alpha, beta, alpha is like my easy. Beta, annoying but doable. Gamma, frustrating but can be managed. Neutron, unstoppable. Now, why is that? Well, here's the deal. You have two charge particle, one energy packet. All three will interact with something. Neutron is neutral. It does not care. It's here's the deal. If you remember from your school days, you must have remember the fact that majority of atom is just empty space. Now, electron cloud is in that empty space, but here's the deal. If you are not charged, it does not exist for you. You can just go through it. So from neutron's vantage point, when neutron is released in fission or fusion, it is going, it's going fast. Now, from its vantage point, nothing exists. Like nothing is there. It just like goes through it. It does not care. Now, here's the worst part of it. If it does interact, let's say some other nucleus comes into its path and gets wabaimed into it, yeah, it is so angry, so powerful that it will make that puppy into radioactive. Like, for example, in case of fission reactors, we have a lot of neutron coming out, which are not very high power neutron, but powerful enough. So we use water as a moderator. Now, water will slow it down, but here's the deal. It's neutron. Neutron will make water radioactive as a vengeance. So let that sink in. Alpha, beta is annoying thing. The moment you have neutron, run. So if you have to deal with basically radioactive decay of alpha, beta, gamma, manageable. Frustrating, manageable. Neutron, yeah, dead. So let that be very clear. So you have two charge particle, one photon packet, another mass. And this puppy, like from its vantage point, everything is just empty space. So it's very hard. And not to mention, when it does hit, it's so angry, it makes other things radioactive, be it water, be it carbon. So And here's the deal, what happens eventually? Let's say you have a source that is giving out all of these force thing and you contain it. What happens to it? It heats up. Eventually, all these things will be translated into atomic vibration, aka temperature going up. So it will turn to heat. You can use that heat to do work for you. That's how nuclear reactor works. If you are like, hey, how the heck Iron Man built his reactor? He was very clever. So what he did not went into this route. Most of the fission will, of course, give you a neutron. Most of the fission will also give you a neutron. However, there is a one critical reaction which we classify as a neutronic nuclear reactor, which gives you, instead of alpha, beta, gamma, it gives you proton. Basically, proton is yeeted out of there, and benefit of that is that's directly convertible. Basically, you have an electromagnetic coil, proton wave going through it, output electricity. No conversion. You do not need to boil water and all that. And proton-boron reaction gives you the ability to have all this without neutron, meaning Tony Stark won't die. Now, do not ask how it's done. That's classified, but that's how he achieved it. And that's why they said palladium rather than boron. Proton-boron reaction, you can research it. Just don't ask how to do it. So alpha, beta is the charge particle. Benefit of that charge particle is the same. You can directly take that charge and convert into useful energy in one step. Source, stuff, electric output. You do not have to boil water and convert or run it into steam. Source, basically like solar panel. That's all it is. Now, people have tried to make solar panels that works on gamma rays, and if we ever crack it, problem solved, but we haven't reached there yet. So how do we achieve basically energy out of beta particle specifically? Is we are utilizing what we call semiconductor junctions. Basically, same way you have P and P junction, same way people figured out, same way we have solar panel, you can build some similar kind of things, and using beta particles, you can get electricity out of it in one stage. Radiation, electricity, done. So that's the core principle of it. And no matter what anybody else talks about, diamond battery, this battery, that battery, all of them will follow this core principle. It cannot be bypassed or broken through. So what are the tools? Well, a tool is, first, in the early days of nuclear technology, we utilized heat, meaning we put plutonium somewhere and we contained it. Now, once you contained it, it starts to heat up. Now, this puppy was injected inside your body. Now, what is inside of the body? You have a blood around you. Benefit of that, that's the coolant. So this is hot, your blood is cold, you have a temperature delta. Utilizing that temperature delta, you have two options. You have Stirling engine option and you have Seebeck effect. So people figured out Seebeck effect has no moving parts, so it will last longer. So Seebeck effect is basically you have two disjunction basically material, and one will be P junction, one will be N type junction, and you'll have heat and you have cold. And the bigger the delta, the more energy you can get out of it. Now, this puppy was not super hot. Of course, you do not want it to boil your blood. So it was very low power. However, it was more than enough power to run basically a capacitor circuit that was regulating your heart rate. And this puppy worked awesome. And the lifespan was 80 years. And yes, this is ancient technology. Now, you may be like, wait a minute, then why the heck in modern today's technology, we have pacemakers and hearing aids and things of that nature where we have to cut open a child and pull it out, put a new battery in? Why? Well, the problem is, while this is awesome technology, it does work. The company that made, if I'm not mistaken, only 100 or 150 pieces were made, like a low order. They were like very clear about it. It's like, go YOLO about your life, but the moment you go poof, please tell us. Do not incriminate, basically turn your body into ash, because that would be radioactive ash. So please, when you pass, make sure we have a way of reaching your dead body and we can pluck it out, because this becomes a company's responsibility. You are talking about radioactive stuff. Nobody did that, and this company is like, out. Like, if you were very thorough with this technology, this would have solved so much unnecessary suffering, especially with children, especially with hearing implants. It's tragic, but I kind of understand it. Actually, I don't understand it. It's like, dude, all they asked is like, once somebody passed, tell them. So that was Seebeck effect, and it was used in space. Apollo mission, it's available in Mars, it's available in Moon, it's available in deep space. So it works. Space RTG is the most common use, and unless you are in Soviet Union, most time you will never encounter RTG. Now, that's using heat. But what if you want to use direct electricity? Using beta particles, as in electron or anti-electrons, you can directly, well, you have electron motion you already have, so why not utilize it? So utilizing that puppy, we made this. This is beta voltaic battery. In this case, it's using helium-3, pardon me, hydrogen-3, tritium. It's using a tritium. And this was also attempted, but I could not verify it, that it was used for pacemakers. Be mindful, the lifespan would be much smaller. Tritium does not last that long. But again, as long as it's there, it won't require you like to recharge it every year. And server clock systems. Servers require a clock cycle that is absolute, meaning it never skipped a bit. If it skips a bit, the security becomes a good luck with it. So for that reason, many companies pay a boatload of money for this sort of instrument where they plunk this battery, turn it on, done. Meaning for 10 years afterwards, they do not even have to worry about like the CMOS battery dying or things of that nature. So it's a tool, it does work, we have utilized it, we have options of utilizing the heat, two primary options, you have Stirling engines and seabag effect. Now like, why don't we use steam? It does not work, it does not have enough temperature delta to justify that architecture. Beta particle has been used, alpha was not that useful, so beta particle, and we have used it to make batteries, which again, in terms of like these things, you can just buy. If you have money, you can just buy it. Now, what's the problem? If this is a thing that we have been working on using, then what's the problem? Well, all of that tech is time tested also, meaning when we are saying that it works, we have tangible data to say that it does freaking work. For example, the RTGs on the Voyager, those are the most respected RTGs ever, simply because those puppies have been working for 45 years. Yeah, 45 years. And that is so far away. Do not say the solar panel. Solar panel will literally start to dip so much that by the time you are crossing Jupiter or Saturn, yeah, good luck with that. So this puppy started with 400 watts of power. The only thing happened is like that 400 watts slowly dropped. And again, as the radioactive isotopes are decaying, you are losing some energy flux also there. So over time, it does cool down. And not to mention degradation of materials, that also causes loss of power. So your heat source is getting cooler, and your efficiency of extraction, that's also going down because of the degradation. Same way a solar panel degrades as you use them. Like that's why the warranty is like 25 years, 80% of the power. They never say after 25 years, if it's dropped to even 90%, we can replace it. 80% because it degrades. So it did degrade, but it did work. With all that jazz, it worked for 45 years. And it's still working, by the way. So again, it's too low power at this point in time to be useful, but it does work. Now, Stirling engine one, that's the heat using seaback effect. But what if using same energy source, but something more efficient? Because be mindful, while seaback effect does have no moving part, does work, those puppies are barely few percent efficient, barely. So NASA did invest a boatload of money into developing free piston engines. These were Stirling engines supposed to work on replacement as of RTG. Now it cannot have spinning parts, it will not last long. So it had to be like free piston that is using air cushion brakes, so to say, basically gas bearings and all that. Nothing is physically touching anything, it's just vibrating back and forth. And it should, in principle, would have worked for centuries, like again, at least decades. But they did build it, and it did work, and it did provide boatload more power, meaning if the electricals were like we only need 400 watt, they would have easily 1/4 the radioactive material needed for the mission. So it does work. Or if you had the same amount of material, you could have increased the oomph coming out of it. However, when they actually built it and tested it, after 146 hours, the power output started to fluctuate and it never stabilized. So, but be mindful, NASA has not abandoned this puppy. It's still research is working on, which they are saying by 2028, we should see something again. There are private companies that are still looking into it. It has some serious potential, especially for a long, not super long duration. Like Voyager is super long duration. But what if you only need it for 10 years? That should be doable. So Stirling engines, while developed, never deployed. Then you have beta voltaics. Again, we use this sort of things. They last for decades. We know this is a tested thing. It has been lasting for 10 years, 20 years. It's a done thing. Unless you are in Soviet Union, where you can just scroll through places and be like, voila, RTG. Because in Russia, we do not care about safety. Safety cares about us. It's like, now all of this gives you an impression that it's a known technology, we use it, it has been in use, then what's the problem? All of them are very weak, all of them. Even this giant puppy is weak. Although in Russia, it does work very well. Why? It's cold. So to get most efficiency in seaback effect, you need large temperature delta. So if we take the same puppy, put it in India, it's not going to work very well. But put it in, Antarctica level places, it's going to be like, power. So that's the whole problem with this. It's like, it's very weak. The energy output of it is tiny, very tiny. It's almost like if you want to run a watch, the battery would be size of a smartphone, big smartphone. If you want to run a smartphone, the battery would be size of a briefcase. If you want to run a car, the battery would be size of a truck. That's the problem. So it's just too weak. Energy is there, let that be very clear. E equal to mc square says that there is more than enough energy. We just can't extract it efficiently enough to justify it yet. So what about the Chinese one? Now Chinese one, a big maybe. Now why is that? Well, core issue is always the same, is the low power of it. So if the company says that we're gonna make this, are there companies making it? Yes. If the company says that we're gonna mass produce it, again, define mass produce. Like mass produce of some things are like, hundreds of units, compared to mass produce of something else would be like millions of pieces. So define that part. But because of the low energy, it's always a niche case, meaning most people have no inherent context of how little is 100 nanowatt or microwatt is. Because here's the deal, to give you a context what this battery is claiming, 3 volt, it's more or less what this puppy can do. A coin cell battery, a lithium coin cell, that is like a 2025 or 2030. It is useful, but not too much. And many case scenario, because it does not have the amp capacity, they suggested put a capacitor bank. So basically, if you have a sensor that is reading all the data, but it needs to send the data over radio, it will consume a lot of power. So charge the capacitor, let's say for 1 hour, and dump the data in, basically run the high power load on that capacitor. So basically off for 1 hour, on for 1 minute. So 12 pings you can get out of a day. So it has some use, let that be very clear. It's not useless. And what the company is claiming, 3 volt, why it's so important? At that voltage, it starts to work with normal stuff. It's just like, oh, it's a stuff, you use it. So you do not have to buy too many of these and put them in series to get useful voltage. So if what they are claiming, the 3 volts and the milliamp capacity, what they are claiming, not milliamp, microamps. So it's actually useful, let that be very clear. But still a niche case. It's not like, oh, and not smartphones, let that be very clear. Now, which elements are the candidates here? This is where it becomes interesting. There are 3 major options that you have available. Others can also be found, but these 3 main options you have. You have nickel 63, gives off a lot of beta particles. You have carbon 14, gives off a lot of particles, but for very long time. And you have hydrogen 3. So depending on your requirement, depending on if you're understanding in semiconductor design, you can select whatever works for you. So what Chinese people are claiming, the closest analog to it is this puppy, where you have nickel 63 and diamond cell, and that's acting as a Schottky junction diode, PNP junction diode, and is giving you electricity. Now, will this work? Yes, this is an old Russian design from 2018, if I'm not mistaken. And yes, the science is there, principle is there, and that was the whole point of it. It was like, whoa, they were actually reaching almost 1 to 2% efficiency. And that's significant. So it does work. So what Chinese designs are putting forward almost looks like they're touching the theoretical maximum of this design. This design should, in principle, touch 5%. At that point, it actually becomes something that every Tom, Dick and Harry can use in something like a Internet of Things devices, or if you have a big brick of it and that charges the capacitor and you do a lot of things, many remote location will be like, shut up, take money. So is it a mass marketable product? Hell no. And rule number 1 of any sort of paperwork, if you cannot find a real photo of it, like in this design, I can find a real photo of it. And diamond cell designs, I can find the physical photo of it. If I never found a physical photo of these things, yeah, that's why big ass maybe. In principle, what they are saying should be doable. With newer junction technology, newer manufacturing technology, we should be able to reach efficiency. And we did the same thing with solar panel. Back in the day, solar panel was like 1% efficient. We switched to silicon, it went to 5%. Then we upgraded more, 10%. Now we are at 25%. So it should be possible in principle. But because of lack of real photos, I'm like, press X for doubt. So that's why I put a big ass maybe into it. Now, this whole system made me very hopeless, because all the headlines that I'm looking into it is like, ditch the charger for. This is a freaking news network. A news network is saying, ditch the charger. I'm like, either the company is trolling, or these people are trolling, or they think everybody else is stupid. It's like, dude, the company is flat out saying it's microwatt. Your phone consumes a boatload of power. Have you ever noticed like how much power we are putting into our mobile phone? A mobile phone requires power banks that are like big, as in like 15 watt power bank, 20 watt power banks, as in like some adapters are like 60 watt for mobile phone. So in that sort of world, you're going to say microwatts of power is more than good enough. I'm like, what are you smoking? Even with capacitor system, that's why I said the battery would be size of a briefcase if you have to do this. So way too many sources called about smartphone, which I'm reasonably sure if the company is real, they would have never, ever said it. At best case scenario, they will say something like this. Now, does it make sense? If the cost is low enough, yes, I can see it as sense, because like, hey, buy this remote, never worry about battery until you throw the damn device away. It's like, shut up, take money. But other than that, no. Now, is it's a breakthrough and all that? No, it was a breakthrough in 1970s when we were first developing this technology. It's like first time we developed LCD, it was like, whoa. A 2D array without having an electron gun, that was like, whoa. Now, OLED is still a big improvement from LCD, but it's not like, whoa. The breakthrough was going from 3D object to make a 2D picture to like actually going a 2D grid array. So it's not breakthrough. Like if you call everything a breakthrough, nothing becomes a breakthrough. So it's not there. Now, are there any possible breakthroughs? Yes. The possible breakthrough is this research paper that I have found, that is from HAL Open Science. Ultra high conversion efficiency of beta voltaic cell using diamond p-n junction. That's why I say like it's a semiconductor. And why people keep focusing on diamond is because it's very easy to grow and very efficient, easy to control the efficiency, how easily it's laying out. And we are talking about layer by layer. So it's a very useful thing. Now, what they have achieved in this paper, what they are claiming is 28% efficiency. Now, let that be very clear. They are very, it's a research paper, whereas like we have thought of it because there is a law, quote unquote. Same way we have a law, like if you have a photon source like sun and you have a single junction solar panel like a semiconductor, it has a theoretical limit. Now, we created a theory based on our understanding of quantum physics and all that. And that says like, brah, no matter what you do, you're not going to cross realistically 30 or 35%. You're not going to reach 50. And then how do we make 50% efficient solar cell? We use multi-junction. Single junction has a law of physics limit. You cannot break it. So same goes with beta voltaic. It's a junction. So inherently there are some laws. So that law is Shockley-Quasar efficiency limit. Now that limit claims around 30%. So what their testing showed, they can almost touch 28%. Now that would be breaking efficiency, because if that statement is true, yes, in a principle, if this statement is true, you can make a battery that is powerful enough to run a smartphone. Low power smartphone, not a high power gaming smartphone, but more than enough where people will be like, and that would be world changing. That would be breakthrough. But again, if we have already used breakthrough for Chinese product, how the heck real breakthrough will happen? So what China has, like because of the voltage claim, because of the milliamp hour claim, the likelihood is they are touching 5% efficiency. Is it doable? Maybe. Not impossible. Let that be very clear. The law of physics does not block it. It's just that, have you actually managed to reach that point? It's like, we knew that we can reach 30% efficiency in solar cells long ago. It's just like, it took us time to reach there. So have China already reached it? I do not know. But all these news articles, overhyping thing, it's bad. It's like, that's why I said, like, if hype is very harmful for hype's sake, if you're just hyping things up, imagine now once this happens, same way we had like few years ago diamond battery and all of this fluffed out, and now companies are filing bankruptcy, other companies are getting investigated for fraud because they're like, dude, you never actually built a damn thing. So every time this happens, now here's the deal. What about these scientists who have actually developed something? Let's just say they are like, hey, we can make an actual product that is, let's say, 25% efficient. That would be significant, but they will never get funding for it because people would be burnt by carbon nanotube diamond battery, people would be burnt by diamond battery, people would be burnt by Chinese battery. That's the problem. You cannot have hype for hype's sake. It has consequences, like serious real world consequences. So coverage of this product, be mindful, at least 1 or 2 scientists have done a very phenomenal coverage with scientific data and all that jazz, which was very good. Some hope, but news article, like people are paid for this, and yeah. So there is some hopeless reality of it, which, what can I do? So this was my presentation on basically Chinese nuclear battery. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.